Hello and welcome back to CS 128 Honors. Today we'll be covering the concept of ownership. If you'd like to read more on today's lecture, you can visit chapter 4.1 of the Rust book. So, ownership. What is it? It is a unique feature to Rust where it's the set of rules that the compiler enforces that manages the memory for you, unlike other languages which we'll cover today. This model makes Rust memory safe without a garbage collector. Okay, so briefly, we'll cover the differences between some memory management protocols. One, stack and heap. The stack is just an area of memory where you add one by one and then you pop it last off the list. This is the easiest. Then the heap needs to manage how memory is stored out of arbitrary sizes and can be freed or allocated in any order. So in a C, there's a stack and there's a heap, and the heap tends to grow up, the stack tends to grow down. But the stack, you can only free it from the end, while the heap, you can free it anywhere in the middle. Since the heap needs to host objects of any size, and anywhere in the heap, it takes time to allocate it, and it's slow to find the variables in the heap. But this does come with the benefit that you can expand it later and add new values in any order. Okay, here's an analogy to help you understand how the heap works. So consider the heap like a restaurant. When you first come in, you come with your group, tell the hostess how many people you need to seat, and then they find a table for you with this many places. Just like in an actual heap, the host does not know how many people you will have until you get to the restaurant. So they need to find a corresponding space for you once you already get there. And it takes time to search through all the tables to find one with enough room for you, just like in an actual heap. So, how to manage memory? We ask the heap for memory based on the size of the object we're trying to allocate. We keep track of where it's stored and how big it is. Then when we're done using it, we free it and return the memory to the heap. So, approach 1 to memory management is to do it all yourself, like in C or C++. You have to take care of where it's allocated and where it's freed. But this can come with lots of problems. Like for example, if you free it before you use it again, then it's called a use after free bug, and the variable is no longer valid and can cause like security concerns. If you never free it, or free like long since you needed it, you're wasting memory, and this is called a memory leak. So a double free is even worse behavior, since you can't really tell what's going to happen, since you're trying to free memory that's already freed. Approach 2 is to do garbage collection. So on your behalf, the language, like Java, manages all the pointers and memory in the backend. Then when it detects that you're done with using it, it automatically frees it for you. High-level languages like Java and Python use this kind of method. What's the problem with this though? It takes extra performance since it costs time to search through all these references that you have to memory on the heap, and then you need to free it manually one by one. Whereas if you did it manually by yourself, then you could improve performance by allocating and freeing wherever you need to. Alright, why are we talking about this? Rust offers a new idea to how to manage memory, which is not seen in any language before it. This idea of ownership helps us manage how we store stuff on the heap without a lot of overhead, since all the comparisons are done on the compiler side. The compiler checks for you whether your program is valid, and if it's not, it doesn't let you compile. Whereas in C, if you have memory leaks, it would compile it for you and you'd have to detect them by yourself down the road. So, what is ownership? Ownership is a set of rules that the compiler enforces on your code. First one is that each value in Rust has an owner. This means, like, for example, if you have a variable that addresses to a space in memory, it can be the only variable that refers to that space in memory, which is part 2. You cannot have multiple variables addressing the same memory location. Then rule 3 is then when you're no longer using the variable, when it's out of scope, the value will be dropped and the memory will be freed. Okay, let's consider this example. This bracket notation indicates the scope of a function. So the scope inside here exists exclusively inside here. So you let a variable s equal hello here. The compiler has this variable. S refers to this value. And once s leaves the scope at the closing bracket, this value is dropped along with the owner. So you cannot use s or hello afterwards. This involves data that also lives on the heap, like a string, for example. This is a variable size array of characters that it's managed for you by the Rust standard library. And you can push more strings and characters onto the string and increase its size. So drop is a special function from Rust that essentially frees the memory, just like free in C or delete in C++. Just like a variable in the stack, like s equals hello before, this string from hello, even though it lives on the heap, when the variable s goes out of scope, Rust will drop the memory stored by string here, and this will no longer exist on the heap, freeing the memory and allowing it to be used for other processes. And the difference between garbage collection and drop is that drop knows exactly where it happened. Drop would happen at this closing brace, whereas the garbage collection would happen at specific intervals during runtime. So it would have to manually check the time, determine whether it should call garbage collection, and then it would call garbage collection. Whereas the drop would always happen on exit of this scope. And it's in the binary without any conditional branches, making it a lot more efficient. So, why would you do this, right? Let's say you have a variable x that's 5, and you set y to x. This looks all right, right? These both are equal to 5, and they're both on the stack. Where this is okay, right? They're just 5. Each can fit in a single register. Whereas here, s1 is a string on the heap, and it stores a pointer to the memory of the string on the heap here. It has a length and a capacity on the stack as well. Then if you let s2 equal s1, you have the s2 pointer point to the same place in memory, which can be a problem, because if you stop using one of them, and let's say you drop it in the future, you'll still have the pointer, but it'll lead to somewhere that was already freed. Like, for example, you want this to happen. You'd think that if it's copied like this, you'd copy the heap value. But since it's a pointer, it doesn't know that this should be copied or not. This doesn't happen. And since it's expensive to just copy over memory, you need to allocate more, copy each byte one by one, and that's a lot of steps. So what would happen, in other languages at least, is they would point to the same heap location. This is still a problem though. What if they go out of scope? You drop one, and you drop the other, right? That means you'll free this pointer twice, which is a problem which we talked about earlier, which leads to undefined behavior. So when you first drop this one, okay, sorry. What actually happens with the compiler is that when it sees S1 is transferred here, it drops the original value or variable S1 and transfers ownership of the heap to S2. So this construct here no longer exists, and it entirely exists in S2. And any later uses of S1 are forbidden by the compiler. Since each value here on the heap can only have one owner. This cannot own it if this already owns it. When you clone it, this forces a deep copy, copying both the stack value and the heap value. This is okay, and when one is dropped, it will not cause a double free error on the other. So, oops. Let's go over ownership rules again. Each value can only have one owner. There can only be one owner each value has an owner, and each owner refers to like a unique variable. Each owner corresponds to one value, and yeah. Okay, let's cover another example here. Let's look at this, right? So this takes ownership function. It takes in the string. Like the example before, it would pass in this, instead of passing S1 to S2, it would pass this S to the takes ownership function. It would be moved here, invalidating S, since ownership of the heap was transferred here, and takes ownership does not return back to the main function. It does not return the ownership back. Whereas for a primitive value like 5 that lives exclusively on the stack, you can copy this as much as you want. There's no heap value to be owned. Whereas here, gives ownership, returns this value some string, and gives it to the S1 value, or S1 variable. The same is said for here. This would be yours, this would be hello. This is essentially the same thing. Then takes and gives back here. Unlike the previous function that just takes ownership, see how nothing is done here at the end of this sum string? Or nothing is done with sum string, unlike here, where you return it back at the end. It returns a string, it just gives back to the original function. So you can take S2 and reassign it to S3. Okay. Hopefully that covered everything you need to know to begin with understanding ownership. Homework 3 is released today. Oops, sorry for the wrong date. It's due on September 30th or 29th at midnight, which should give you 7 days, including today. Okay, thank you for listening.